You take a ball, you rotate it 360 degrees. One full turn, the ball returns to its starting position. Everything makes sense. Everything works the way it should. Now you take an electron, you rotate it 360 degrees, one full turn, and the electron does not return to its starting position. It becomes the opposite of itself. Minus becomes plus. Up becomes down. To return the electron to its true starting state, you need two full rotations. 720 degrees, not 360. 720. This is not a joke. This is not a measurement error. This is a fundamental property of electrons and every other particle that makes up matter in this universe. Richard Feynman, one of the smartest physicists of the 20th century, spent years trying to explain this to students. He would stand at the blackboard with his diagrams and his equations, and eventually he would stop. He would turn to the class and he would say something like this: if you think you understand electron spin, you don't understand electron spin. Nobody does. We can calculate it perfectly. We can predict every experiment. But understanding it, actually grasping why nature works this way, that's still beyond us. The property is called spin. Terrible name, really. Because it suggests the electron is spinning like a top, rotating on an axis. But that's not what's happening. The electron is not rotating. It cannot be rotating. Here is why. Electrons are point particles. They have no size, zero radius. If something has no size, it cannot rotate because there is nothing to rotate. Rotation requires a surface. The electron has no surface. It is a mathematical point, and yet it behaves exactly as if it were spinning. It has angular momentum. It creates magnetic fields. All the things a spinning charged object would do. The electron does them without actually spinning. This drives people insane. It drove Einstein insane for a while. It drove an entire generation of physicists to the edge of what language can describe. Because here is the problem. We have a word, spin. And that word carries meaning. It carries images, a top spinning, a planet rotating. But when you apply that word to an electron, none of those images work. The electron is not a tiny sphere rotating on an axis. It is not anything you can picture. It just has a property, a number. And that number behaves mathematically like angular momentum. But it is not angular momentum from rotation. Scientists discovered this in the 1920s. Two physicists, Gaudsmit and Uhlenbeck, they were trying to explain some weird results from experiments with atoms. The electrons in atoms were doing things that didn't make sense, creating magnetic fields that shouldn't exist, splitting into multiple states when you put them in a magnetic field. The math only worked if you gave the electron an extra property, angular momentum that came from nowhere. They called it spin because they didn't have a better word. And the name stuck, even though it's wrong. Feynman hated this. He hated that we use everyday words to describe quantum properties, because everyday words come with everyday meanings, and quantum mechanics does not work like everyday life. When you say spin, people picture rotation. When you say wave, people picture water. When you say particle, people picture a tiny ball. All of these pictures are wrong, but we are stuck with them because we evolved to understand balls and waves and rotation. We did not evolve to understand quantum mechanics. Our brains are not built for it. But here's what makes electron spin truly bizarre. It is not just that the electron has this property that looks like rotation, but is not rotation. It is how that property behaves when you turn the electron. In classical physics, if you rotate something 360 degrees, you get back what you started with. Always. This is not a law. This is geometry. A full circle brings you back to the beginning. But an electron does not follow this rule. Rotate an electron 360 degrees, and its quantum state picks up a negative sign. The wave function that describes the electron flips. Plus becomes minus. You need to rotate it 720 degrees, 2 full circles, to actually return to the starting state. This is not a quirk. This is fundamental. Electrons are what mathematicians call spin 1/2 particles. The 1/2 means their spin angular momentum is 1/2 of the basic quantum unit. And that 1/2 has consequences. It means they transform differently under rotation than anything in our everyday experience. They do not live in normal three-dimensional space. They live in a mathematical structure called Spinor space. And in Spinor space, a full rotation is not enough. You need 2. There is no way to visualize this. None. You cannot draw a picture that makes it intuitive. The best physicists in the world have tried. Feynman tried. Dirac tried. They came up with clever demonstrations, belt tricks, plate tricks, ways to show that you can twist something twice and get back to the start. But these are analogies. Shadows. The real thing happens in mathematics and equations. In a space that does not correspond to anything you can see or touch or point to. And yet we can measure it, we can do experiments, we can put electrons in magnetic fields and watch them split into 2 states, spin up and spin down. We can rotate them and measure how their quantum state changes. The predictions match the experiments to extraordinary precision. The math works. The theory is correct. But ask any physicist what spin really is. Ask them what it means for an electron to have this property. You will get silence or you will get math. You will not get an answer that satisfies your intuition because there is no such answer. The story of how we discovered electron spin is a story about being forced to accept something impossible. In 1922, physicists had a problem. They were studying atoms, shining light on them, putting them in magnetic fields, and the atoms were not behaving correctly. The spectral lines were splitting, creating patterns that should not exist. Math said each electron in an atom should produce 1 line, but experiments showed 2 lines, always 2. Something was missing from the theory. 2 young physicists in the Netherlands decided the electron must have an extra property. George Uhlenbeck and Samuel Goudsmit, they were graduate students, nobodies. But they did the calculation. If the electron has intrinsic angular momentum, if it acts like it is spinning, even though it is not actually spinning, then the math works. The 2 lines appear. Everything fits. They wrote up their idea and showed it to their supervisor, Paul Ehrenfest, a respected physicist, someone who knew the field. Ehrenfest read their paper. He thought about it. Then he told them not to publish it because it was obviously wrong. The electron cannot be spinning. If you calculate how fast a point particle would need to spin to produce the measured magnetic field, you get an impossible answer. The surface of the electron would need to be moving faster than light, and nothing moves faster than light. The idea was dead, it could not work. Uhlenbeck and Goudsmit agreed. They decided to drop it. But Ehrenfest had already sent the paper to a journal, as a joke almost, to see what people would say. And before they could stop it, the paper was published. And immediately, physicists everywhere started testing the idea. And it worked. Every experiment, every prediction. The electron really did have this extra angular momentum, somehow. Even though the calculation said it was impossible, nature did not care about the calculation. Nature did what it wanted. This is a pattern in quantum mechanics. Theory predicts something that seems absurd. Physicists reject it then experiments force them to accept it anyway. Wave-particle duality, uncertainty, entanglement, superposition. All of these started as ideas that seemed obviously wrong, and all of them turned out to be correct. Electron spin was just another item on the list, another piece of evidence that the universe at its deepest level does not match our intuitions about how things should work. But electron spin was special because it was not just weird. It was geometrically weird. It was not about probability or waves or any of the other strange features of quantum mechanics. It was about rotation. Something we understand, something simple. You turn an objectator, it comes back to where it started, except when the object is an electron. Then it does not come back, not after one turn. You need two. Wolfgang Pauli figured out the mathematics. He was one of the most brilliant physicists of his generation, notoriously critical. He would sit in lectures and mutter, "This is wrong," whenever someone made a mistake. But man, he made very few mistakes himself. Pauli showed that if you describe the electron using a mathematical object called a spinor instead of a normal vector, then everything works. Spinors transform differently under rotation. They pick up that negative sign after 360 degrees, and they return to their starting value after 720. This was 1927, the same year Heisenberg published the uncertainty principle. The same year the Copenhagen interpretation was being argued over, quantum mechanics was coming together. And at the center of it was this strange fact: particles have spin. And spin does not work like anything else in physics. It is not something particles do. It is something particles are. An intrinsic property like charge or mass, except charge and mass make sense. You can picture them. Spin does not make sense. Wow. You cannot picture it, and yet it is real. Paul Dirac took it further. In 1928, he wrote down an equation, the Dirac equation. It describes how electrons move and behave when you combine quantum mechanics with special relativity. And out of that equation, completely naturally, without putting it in by hand, electron spin appears. The equation predicts it. Spin 1/2 magnetic moment. Everything. Dirac did not add spin as an extra assumption. It was already there, hidden in the structure of space-time and quantum mechanics, waiting to be found. This shocked everyone, including Dirac. He had been trying to make quantum mechanics consistent with relativity. He succeeded. But as a bonus, his equation told him that electrons must have spin, and not just any spin, exactly the spin that experiments measured. This was not a coincidence. It was a hint, a clue. It meant that spin was not some random property tacked onto the electron. It was fundamental, built into the fabric of reality, a consequence of how space and time and quantum mechanics fit together. But even Dirac could not explain what spin is. He could calculate with it. He could predict experiments. His equation is one of the most successful in all of physics. But if you asked him, what does it mean for an electron to have spin 1/2, he would not have an answer. Not a satisfying one. He would point to the math. He would show you the spinor. He would demonstrate how it transforms. But that is description, not explanation. We know how spin behaves. We do not know what it is. Feynman came along later, 1940s and 50s. By then, spin was well understood mathematically. But Feynman was obsessed with understanding, not just calculating. He wanted to know what things meant, why they worked. He spent years thinking about spin, trying to find a way to explain it that did not rely on abstract mathematics. He invented all sorts of visual aids, diagrams, analogies, little tricks to help students grasp the idea. None of them worked, not really. They gave you a flavor, a sense, but they did not give you understanding. And eventually, Feynman gave up. He accepted that some things in quantum mechanics cannot be understood in everyday terms. They can only be described. You learn the math, you do the calculations, you predict the experiments, and you stop asking what it really means, because there might not be an answer to that question. Or if there is an answer, it might be in a language humans do not speak. This bothered Feynman until the end of his life. He hated not understanding. But he also respected the evidence. And the evidence said the spin is real. Spin has consequences. You can measure it. You can use it. Magnetic resonance imaging in hospitals, quantum computers, spintronics. All of these technologies work because electrons have spin. The property is not abstract. It is concrete. It changes the world, even if we do not fully understand what it is. So what exactly happens when you rotate an electron? Let's be precise. In quantum mechanics, particles are described by wave functions, mathematical objects that encode everything you can know about the particle: position, momentum, energy spin. When you rotate a particle, you rotate its wave function. You apply a mathematical operation, and the wave function changes. For most objects, this is simple. Rotate 360 degrees and the wave function comes back to itself, unchanged. But for spin 1/2 particles like electrons, it does not come back. It comes back multiplied by -1. Every value in the wave function flips sign, plus becomes minus. Minus becomes plus. The wave function is opposite to what it was. And if you rotate another 360 degrees, it flips again back to the original. 2 rotations, 720 degrees. That is what it takes. Now you might think this does not matter. If the wave function is multiplied by -1, but everything else stays the same, who cares? The negative sign is just math. It does not change anything physical. And for a single isolated electron, you would be right. The negative sign does not change any measurement you can make. Probabilities depend on the square of the wave function, and squaring removes the sign. -1 squared is +1. So a single electron rotated 360 degrees looks identical to an unrotated electron. You cannot tell the difference. But here is where it gets interesting. The negative sign does matter when you have multiple particles, when electrons interact, when they form systems. Then the relative signs between their wave functions become important. This is how chemistry works. How molecules form. The way electrons combine in atoms depends critically on their spin and how their wave functions interfere. And interference depends on signs, plus and minus. If you rotate one electron but not another, the relative sign changes, and that changes the system. That changes reality. This is not theoretical. This is measurable. There are experiments called interference experiments where you split an electron into 2 paths. Send one path on a journey where it gets rotated 360 degrees. Send the other path straight. Then recombine them. And you see interference. The 2 paths cancel or reinforce depending on their relative phase. And the path that got rotated picks up that extra negative sign. You can see it. You can measure it. The 720-degree property of electrons is not abstract mathematics. It is physical reality. Mathematicians have a name for objects that behave this way: spinors. They live in a space that is sort of draped over ordinary three-dimensional space. When you rotate in ordinary space, the spinor rotates in its own space. And one full rotation in ordinary space corresponds to half a rotation in spinor space. That is where the negative sign comes from. You have not completed a full cycle in spinor space yet. You need 2 turns in ordinary space to complete. 1 turn in spinor space. This sounds like word games, like abstract nonsense, but it is not. Spinor space is real in the sense that it makes predictions. It tells you how particles will behave, and those predictions match experiments perfectly. The mathematics is not a trick. It is a description of how nature actually works. And nature works in a way that requires this double covering, this strange relationship between rotations and quantum states. Feynman tried to make this intuitive. He came up with demonstrations. One famous example: take a belt, attach one end to a fixed point, hold the other end in your hand. Now rotate your hand 360 degrees while keeping the belt attached. The belt gets twisted, tangled. But if you rotate your hand another 360 degrees, 720 total, you can untwist the belt without rotating your hand back. The belt returns to its starting configuration even though your hand is rotated twice. This is supposed to be an analogy for electron spin, but it is not a good analogy. It is a topological trick. Yes, it shows that some systems need 2 full rotations to return to their starting state. But the belt is not a spinor. The reasons it behaves that way are completely different from the reasons an electron behaves that way. The belt trick is classical. Electron spin is quantum. They are not the same. Feynman knew this. He admitted the analogy breaks down, but he kept using it anyway because he had nothing better. The truth is, there is no classical analogy for spin. None that works, because spin is fundamentally quantum. It emerges from the marriage of quantum mechanics and relativity. Dirac's equation shows this. When you write down the equation that describes how a quantum particle moves in a relativistic way, you discover that the particle must have 2 components, spin up and spin down. You cannot avoid it. The math forces it on you. And those 2 components transform as a spinor. They pick up that negative sign under rotation, not because of any mechanism, not because of any hidden gears, just because that is how the math works. And the math works because that is how the universe works. There's something deeply unsettling about this. We want to understand things in terms of mechanisms, gears, causes, things pushing other things. But quantum mechanics does not work that way. Properties just are. They exist. They follow rules. But the rules are mathematical, not mechanical. Spin is not caused by anything. It is not the result of some process. It is an intrinsic property. It comes with the electron. Part of what it means to be an electron is to have spin 1/2. And part of what it means to have spin 1/2 is to transform in this strange way under rotations. This is what Feynman meant when he said nobody understands quantum mechanics. Not that the math is too hard. The math is fine. Generations of students learn it. They calculate with it. They get jobs using it. But understanding, actually grasping what the math represents, what it means for reality to be this way, that is different. That is still out of reach. We know the rules. We do not know why the rules are what they are. We do not know what the rules are rules about. At the deepest level, quantum mechanics is a black box. Input experimental setup, output prediction. And the predictions are always right, but the box itself remains mysterious. Spin is perhaps the purest example of this mystery, because it is so simple. 1 number, 1/2. And yet that one number encodes a truth about the universe that defies everyday intuition. Rotations do not work the way you think they work. Not at the quantum level. Objects are not what you think they are. Space itself might be something different than you imagine, and we know all of this because we measured electrons, tiny invisible point particles, and we found that they transform in a way that requires 720 degrees to complete a cycle. And nobody knows why. So here we are. Electrons have spin. Spin is not rotation. Spin requires 2 full turns to return to the starting state. We could use it to build technology, and we have no idea what it really is. This is not a failure. This is science working correctly. Science is not about why. Science is about how. How do electrons behave? How do you predict their behavior? How do you test those predictions? The answer to all of these questions is clear. We know how. We have equations. We have experiments. The match is perfect. But the why? Why does nature choose these rules and not some other rules? That question might not have an answer, or if it does, the answer might be buried so deep that we cannot reach it. Not yet. Maybe not ever. Feynman made peace with this. Late in his life, he stopped trying to find intuitive explanations for quantum mechanics. He accepted that the universe is stranger than human intuition can grasp. We evolved to throw spears and find food and recognize faces. We did not evolve to understand point particles with intrinsic angular momentum that transforms under double rotation. The fact that we can understand it mathematically is already remarkable, maybe even miraculous. Asking for more, asking for intuition, that might be asking too much. But the mystery remains, and it is not just about electrons. Every fundamental particle with half-integer spin behaves this way. Quarks, neutrinos, all of them need 720 degrees. Meanwhile, particles with integer spin like photons behave normally. 360 degrees is enough for them. Why the difference? What makes half-integer spin special? Nobody knows. There are mathematical reasons. Group theory, representation theory. You can write down the structures and show that this is how it must be, but that is just pushing the mystery back one level. Why does nature use these mathematical structures and not others? Some physicists think the answer lies in deeper theories. String theory, loop quantum gravity, theories that try to explain why the universe has the properties it does. But these theories are speculative, unproven. They might be right, they might be completely wrong. And even if they are right, they will probably just replace one mystery with another. Why strings? Why loops? Why those structures instead of something else? At some point you hit bottom. You reach the place where all you can say is, this is how it is. And maybe that is okay. Maybe the universe does not owe us explanations. Maybe reality just is what it is, a collection of rules, patterns, mathematical structures. We can discover them, we can describe them, we can use them, but understanding them in some deep intuitive sense, that might be impossible. The universe was not built for our convenience. It was not designed to make sense to creatures like us. We're lucky we can figure out as much as we have. Electron spin is a reminder of this. A reminder that reality is alien, not in the sense of being unfamiliar, in the sense of being fundamentally different from anything we experience. Electrons are not little balls. They are not spinning tops. They are not anything you can picture. They are quantum objects. And quantum objects follow quantum rules. And quantum rules are strange. They are mathematically beautiful. They are experimentally verified. But they are not intuitive. They will never be intuitive, because intuition comes from experience, and we do not experience the quantum world directly. This is what Feynman discovered, or maybe accepted is a better word. He did not discover new facts about electron spin. The facts were already known. What he discovered was the limits of explanation, the boundaries of what can be made intuitive. He tried harder than almost anyone to find ways to explain quantum mechanics in everyday language, and he failed. And that failure taught him something important. Some things cannot be translated. Some truths exist only in mathematics. And if you want to understand those truths, you have to learn the language. You have to stop asking for pictures and start working with equations. But even then, even when you master the math, even when you can calculate anything you want, there is still something missing, a sense of why, a feeling of comprehension. And that is what we do not have. That is what electron spin denies us. We know everything about how it behaves. We know nothing about what it is. And that gap, that space between behavior and essence, that is where the mystery lives. That is where physics meets philosophy, and that is where our understanding ends for now.